All right, let's dive deep into this Paxos thing.
Paxos?
Yeah, the Paxos algorithm.
Okay.
It's got a bit of a reputation for being, I don't know, a bit of a head scratcher.
Yeah, a little bit.
But the funny thing is, the core idea is actually pretty straightforward.
Yeah.
And we're going to unpack all of that today, right?
Yeah.
Using Leslie Lamport's paper, Paxos Made Simple.
That's the one.
Which the title itself kind of gives you a hint.
It does.
That maybe it's not as bad as people say.
Right.
And by the end of this, hopefully you'll have a good grasp of how this, really important algorithm helps computers agree on, well, pretty much anything.
Yeah. And it's amazing, how something that can seem so like, intimidating or like this really complex concept is actually what's kind of run a lot of the stuff under the hood in our digital world.
Totally.
And it's all about making sure that even when things go wrong, right, like messages get lost or computers crash, critical systems can still make these reliable decisions.
Right. So we keep saying the word consensus, right?
Yes.
What exactly are we talking about when we say consensus?
So imagine, you've got this network of computers.
Okay.
Right? They're spread out, maybe across like a data center.
Yeah.
Or even the whole globe, right?
Right.
But they need to work together as one system.
Okay.
So these computers, they need a way to agree on things.
I got it.
Like, what's the next step in a process? Or what's the current state of some data, right?
Okay.
Reaching that agreement, that's what consensus means.
Got it.
In the computer world.
Okay, so it's not just like polling the computers and seeing who says what.
Yeah, it's not a simple vote.
Right.
Right. Things get a little tricky when you factor in all the realities of distributed systems.
Right, because like you were saying,
exactly,
messages get lost.
Yeah, what if a computer crashes in the middle of a vote?
Right.
Or a message with like really important info gets lost in the network.
Yeah.
So what Paxos gives us is this set of rules that make sure everyone stays on the same page, even with all these potential problems.
Okay, so I'm intrigued. How does it actually work?
Yeah.
Like, does it lay out like a voting system or something?
It does. It's a voting system.
Okay.
But it's got this clever twist.
Okay.
It uses this two-phase approach to guarantee that only one value, only one decision actually wins.
Oh, okay.
It's kind of like, setting up a system where everyone agrees on the rules of the game before any votes are even cast.
Okay, that's interesting. So walk me through it.
Okay.
What are the two phases?
All right, so phase one, we call this prepare and promise.
Prepare and promise, all right.
So in this phase, one of the computers, it acts like a proposer.
Okay.
It announces that it wants to, propose a value.
Okay.
And it asks all the other computers, which are called the acceptors, to basically promise that they won't accept any proposals.
Okay.
With lower numbers than what this proposer is putting forward.
Okay, so it's like establishing like a hierarchy.
Exactly, yeah.
Where like the bigger number always wins.
Yeah, a higher number trumps a lower number every time.
Okay.
So this helps prevent confusion, right?
Right.
If messages arrive out of order or if some computers are like temporarily offline.
Right, because things are going down all the time.
Yeah.
So you need to be able to like come back up and know where you are.
It's all about consistency.
Gotcha.
So even if a computer like crashes and comes back online, it can quickly get back up to speed by checking what's the highest proposal number out there and knowing that anything lower than that is basically irrelevant.
That's clever.
Yeah.
Okay, so everyone's made their promises.
Right.
What happens next?
So then we move to phase two.
Okay.
This is called propose and accept.
Propose and accept. Got it.
This is where the actual decision happens. So if our proposer, right, from phase one, if they've gotten enough promises.
Like a majority?
Yeah, a majority's on their side.
Okay.
Then they can formally propose their value.
Okay.
And then the acceptors, they get to decide based on the promises they made earlier whether or not to accept this value.
Gotcha.
And here's the key. A value is only chosen, like officially chosen, when a majority of the acceptors have said yes.
Okay.
They've accepted it.
Gotcha.
And that majority rule, that's super important.
Okay.
Because it means that even if some computers fail, the system can still reach a consensus.
Got it.
You don't have a single point of failure that can bring the whole thing crashing down.
Right, because there's enough redundancy.
Exactly.
That if one goes down, it can keep chugging along.
The system can keep making decisions.
Okay, that makes sense.
Yeah.
So we've got proposers suggesting values, acceptors voting on them. Yeah. Majority rules. That's all starting to make sense.
Great.
But how do the other computers, right?
Ah, yeah.
The ones that aren't directly involved in the voting,
right.
How do they know what the outcome is?
That's where the learners come in.
The learners, okay.
Yeah, so the learners, they're the ones that need to figure out, okay, what value has actually been chosen?
Gotcha.
And Paxos is actually pretty flexible here.
Okay.
It allows for different approaches,
okay,
depending on, what the system needs.
Okay, I'm all ears.
So one way is direct communication.
Yeah.
Each acceptor who votes, yes, can just directly tell all the learners, hey, this is what we chose.
Right. Just tell everybody.
It's fast.
Okay.
But it can generate a lot of network traffic.
Right. Especially if you have a lot of...
Especially if you have a big system.
Computers.
Yeah.
Okay, that makes sense. Are there other ways to do it?
There are. So another way is to pick one computer.
Yeah.
And say you're the designated learner.
Oh, okay.
You're the spokesperson.
Okay.
So all the acceptors, they report their votes.
To that one.
To that designated learner.
Okay.
And then that learner tells everybody else.
Interesting. So there's less chatter.
Right. Less network traffic.
But more risk if that one computer goes down.
That's the trade-off. Exactly.
Okay.
And that actually brings us to another really clever part of Paxos.
Okay.
What if, for whatever reason, a learner just never gets the message?
It's possible?
Right. So Paxos allows a proposer to basically force a decision by issuing a new proposal.
Okay.
And this basically forces everybody to reconfirm.
Okay,
what is the value that we actually chose?
So even if there's like a hiccup,
Exactly.
it's got a backup mechanism to get everyone on the same page?
It's built in. It's like a self-healing system.
That's pretty cool.
Yeah, so even if there's a little problem in the learning process, Paxos has this built-in way to get things back on track.
This is all starting to come together. I like it.
Good.
I have a question, though.
Yeah.
In all this talk about proposers and acceptors, is there someone, like, calling the shots?
Ah, that's where the leader comes in.
The leader.
Yeah, the distinguished proposer. Or as we like to say, the leader.
Oh, okay. Tell me more.
So Paxos works best when there's one proposer, this leader, who's in charge of starting all the proposals.
Yeah.
It's kind of like having a conductor.
Right.
Leading an orchestra.
It makes sense.
It prevents chaos.
Yeah.
Everyone's moving in sync.
So you don't have, like, competing proposals, like, flying around?
Yeah, you don't want these endless cycles of back and forth.
Okay, so that makes sense, but what happens if the leader goes down?
That's a great question.
Does the whole system just stop?
No, the system actually remains safe.
Okay.
Any values that were already chosen, they stay valid.
Oh.
But to make sure things keep moving forward, you need to elect a new leader.
Okay, so that's a whole other can of worms.
That's a whole other deep dive.
Ooh, I'm liking it.
Yeah.
Okay, so we've got this, like, really robust system for reaching consensus.
Right.
Even when things are uncertain.
Yeah.
But I have to ask, why should we care?
That's the big question. Right?
Yeah, is this just some, like, theoretical thing?
Yeah.
Or does it actually have, like, real-world implications?
It's not just theoretical. It's actually running a lot of the systems that we rely on every day.
Really?
Yeah, think about distributed databases.
Right.
These things store massive amounts of data across multiple servers.
Right.
Paxos is what makes sure that all those servers agree on what the data actually is.
Got it.
It guarantees that it's consistent.
So, like, our online banking, our shopping, social media, all that stuff
all that
is relying on this.
Yep, it's all running on systems that need to agree.
Wow.
And Paxos is often the one making sure they do.
Okay, that's pretty crazy. So it's like a silent guardian working in the background?
Yeah, that's a good way to put it.
To keep our digital lives running smoothly.
It's a hidden hero.
Yeah, and I feel like this is giving me, like, a whole new appreciation for how this, kind of complex algorithm solves such a fundamental problem.
Yeah, it's a really elegant solution to a really hard problem.
Totally.
Yeah.
Okay, so before we wrap up this part, I want to leave our listeners with a question.
All right, shoot.
So we know that Paxos ensures computers can agree.
Yeah.
But what about us humans?
Oh, that's interesting.
Right.
Yeah.
Like, can we learn anything from this algorithm?
Right.
Can we apply it to our own decision-making?
That's a good question.
Especially, we live in a world where information's flying around.
Yeah. So much information.
Opinions everywhere.
It's overwhelming.
Right. So is there something from Paxos that we can learn?
It makes you think.
Right.
Yeah, the principles of agreement and collaboration, those are really essential in any complex system.
Totally.
Whether it's a network of servers or a society of people.
It's true. It's true. Lots to think about.
Lots to ponder.
Okay, so join us for part 2.
Yeah.
Where we'll continue exploring this whole fascinating world of Paxos.
Looking forward to it.
All right.
Welcome back to our deep dive on Paxos.
Glad to be back.
So last time we were talking about the leader, right?
Yes, the distinguished proposer, the leader.
And how important that is for the whole process.
Absolutely.
But the paper kind of hints that it gets a little more, I don't know.
Yeah, a little more real world, right?
Yeah.
A little more complicated when you actually want to build this.
Exactly.
Mm-hmm.
So what are some of the challenges of actually putting Paxos into practice?
Well, one of the big ones is that the paper talks about these processes as proposers, acceptors, learners.
But in the real world, these processes are often running on separate physical machines like servers.
Ah, okay.
So you might have one server that's acting as a proposer for one decision.
Okay.
And then an acceptor for another decision.
So it's not like...
And a learner for another one.
One computer, one role.
Right. It's not that simple.
Okay.
And to manage all this, complexity, the paper suggests electing one server as the leader.
Okay.
And this leader becomes the main proposer.
Okay.
It's like having a conductor.
Right. We talked about
leading the orchestra, making sure everyone is in sync.
Okay. So the leader keeps things organized.
Right.
But I'm a little confused about this idea of instances.
Yeah.
Of the Paxos algorithm. What exactly does that mean?
So it's not about having multiple copies of Paxos.
Okay.
It's about applying Paxos to a series of decisions.
Oh, okay.
One after the other.
Okay.
So each decision gets its own instance of the algorithm. And this is how Paxos can help build what's called a state machine.
A state machine, okay.
Yeah, it's basically a system that transitions from one state to the next.
Okay.
Based on these commands.
So each instance is like a single vote.
Exactly.
Deciding the next step in a process.
Yeah, think of it like a game of chess.
Okay.
Each move leads to a new state of the board.
Right.
Paxos makes sure all the computers agree on each move.
Gotcha.
So they all have the same view of the game.
So it's not just making one decision. It's helping a whole system make a bunch of decisions.
That's right.
In a row.
In a consistent and reliable way.
Okay, and to do that, it needs what's called stable storage.
Stable storage, yes, very important.
What is that?
So imagine a computer crashes.
Yeah, happens all the time.
Right in the middle of a Paxos process. When it comes back online, it needs to remember what it promised.
Right.
What proposals it accepted.
Okay.
Stable storage, this is usually like disk storage.
Okay.
Make sure that this critical information isn't lost.
Even if the power goes out.
Even if the power goes out, exactly.
So it's like writing stuff down in a notebook so you don't forget.
That's a good analogy.
Even if you, blank out for a minute.
Paxos needs this kind of memory.
Okay.
This persistence.
Gotcha.
To handle these real-world situations.
Right, where computers crash and
exactly.
messages go missing and stuff.
It guarantees the process can keep going no matter what.
Okay, that makes sense.
Yeah.
Now, the paper also mentions this thing about unique proposal numbers.
Right.
Why is that so important?
So remember, Paxos uses these proposal numbers to prevent conflicts, to establish this order.
Yeah.
If you had two proposals with the same number, it would be chaos.
Right, that would be...
So Paxos prevents that by giving each proposer its own range of numbers it can use.
Okay.
It's like giving each server its own section in a giant number book.
So it's like giving kids in a class their own set of crayons so they don't fight over the same colors.
That's a great analogy.
Okay, so we've talked a lot about the computers, proposers, acceptors, all that.
Right.
But what about the clients?
Good point.
The ones actually using the system?
Yes, the user.
How do they interact with Paxos?
So remember, the ultimate goal is to handle these client commands.
Okay.
Clients submit their requests to the leader.
Okay.
And the leader's job is to figure out where each command fits in the overall sequence of operations.
So the leader's like a project manager.
Exactly.
Keeping track of all the tasks.
Yeah. Let's say a client wants to do operation number 135.
Okay.
The leader will try to get that command chosen as the value.
Okay.
For instance, 135 of the Paxos algorithm.
So if it succeeds, everyone agrees that's the 135th operation that needs to happen.
That's the order of things.
Got it. But what happens if, let's say, the leader crashes?
This is where the resilience of Paxos really shines.
Okay.
Even if the leader crashes, a new one will be elected. And it will pick up where the old one left off.
Okay.
The key here is that Paxos separates choosing a value from actually proposing it.
Okay.
So the new leader doesn't have to start from scratch.
It's like having a backup conductor.
Yes, perfect analogy.
Ready to go?
Ready to step in.
Okay.
The new leader can learn about any commands that were already chosen.
Right.
And figure out what needs to be proposed for any missing spots.
It's like solving a puzzle.
Exactly.
Filling in the missing pieces.
Keeping the order.
Okay, so Paxos can handle that.
It can handle it.
I'm impressed. It's designed for it.
Can the new leader propose new commands right away?
That's a great question.
Or does it have to wait for all the old ones to be finished?
So the paper actually says that a leader can get ahead by proposing commands for future instances.
Oh, interesting.
Even before earlier commands are done.
So it's like a chef prepping ingredients.
Yes. Love that analogy.
For later dishes while something's cooking.
Exactly. Working ahead.
This is important for efficiency.
Yeah, you don't want to be just sitting around.
You don't want to wait for everything to finish before you start the next thing.
Gotcha. So you can work ahead, but
there's a catch.
Okay, there's always a catch.
This means you might end up with gaps in the sequence of commands.
Right, because if the leader crashes...
Especially if the leader crashes...
Before those commands are accepted.
Before everything's finalized.
Okay, so there might be holes in the sequence.
Right, but Paxos has a way to deal with this.
Okay, of course it does.
The new leader will find these gaps and propose special no-op commands.
No.
Yeah, these are basically placeholders.
Okay.
They don't actually do anything.
Gotcha.
They just maintain the consistency of the sequence.
So it's like using a blank tile and Scrabble.
Exactly.
To make a word work.
Perfect analogy.
Okay.
It's all about keeping things in order.
So even if some proposals get lost, you can still execute the commands.
In the right order.
In the right order. That's amazing.
It's well designed.
It's like, I don't know.
Yeah.
A master organizer, right?
It is. It keeps everything in line.
Even when things get messy.
It's very good at handling those messy situations.
And that's what makes it so useful in the real world.
Exactly. Think about databases.
Yeah.
You might need to add or remove servers.
Right.
Paxos can manage those changes without missing a beat.
So it's not just about making decisions.
Right.
It's about adapting.
It's about adapting to change.
To changing circumstances.
It's like a well-oiled machine.
Yeah.
That can adjust to new parts and keep running.
I like it. Okay, so we've covered a lot.
We have.
The basics of Paxos, how it's implemented.
The nitty-gritty.
All of that.
Yeah.
But I have to wonder, is there ever a situation where Paxos can't reach consensus?
That's a good question.
It seems like it can handle anything.
It's pretty robust, right?
Yeah.
But there are some fundamental limits to consensus in these distributed systems.
Okay, like what? Is there anything that can, I don't know, throw a wrench in the works?
Well, it's true. Paxos is incredibly robust.
Yeah.
But there are some, fundamental limits to consensus in distributed systems in general.
Okay.
And remember we were talking about how messages can get lost or delayed?
Right. That happens all the time.
Well, there's this famous result in computer science.
Okay.
It's called the Fisher-Lynch-Patterson theorem.
That's a mouthful.
It is. We usually just call it FLP for short.
FLP, got it.
But what it basically proves is that in a system where messages can be delayed indefinitely, it's impossible to guarantee both safety and liveness.
Okay, hold on. Back up.
Yeah.
Safety and liveness.
Right.
What are those?
So safety means that the system will never choose inconsistent values.
Okay.
It'll never make a wrong decision.
Got it.
Liveness means that it will eventually make a decision.
Okay.
It won't just get stuck forever.
Right. So you're saying there are situations where Paxos might not be able to make up its mind?
It's not quite that Paxos can't make up its mind.
Okay.
It's more like it highlights the importance of understanding the assumptions behind any algorithm.
Right. Because you're assuming that things will work a certain way.
Exactly.
Okay.
So Paxos guarantees safety.
Okay.
It will never choose inconsistent values.
Gotcha.
But in some really extreme scenarios, like where the network is super unreliable, it might get stuck.
Oh, okay.
Unable to reach a decision.
So it's like a group of friends trying to decide where to eat.
Exactly.
And they just argue forever.
And they never pick a restaurant.
Never pick a restaurant. Okay.
And this is where the leader election process we talked about before.
Right.
Becomes super important.
Okay.
If you can elect a leader reliably. And the network isn't, completely falling apart.
Right.
Paxos will pretty much always reach a decision.
Okay.
But FLP tells us that there's no foolproof way to guarantee that will always happen.
Okay, so it's not magic.
It's not magic, no.
It's really well designed.
It is.
But it can't completely escape
Right.
The realities of distributed systems.
Yeah, the inherent challenges.
Gotcha.
And that's why in real-world systems, people who implement Paxos, they often add in extra mechanisms like timeouts and leader leases to help the system make progress.
So it doesn't get stuck.
So it doesn't get stuck in that infinite debate.
Right, like my friends trying to pick a restaurant.
Exactly.
Okay, so it's like adding a bit of practicality.
Yeah, a bit of real-world pragmatism
to
that beautiful theory.
All right, this has been super insightful.
Glad to hear it.
We've gone from like the basics of Paxos.
Yeah, the building.
All the way to its theoretical limits.
We've covered a lot of ground.
I'm curious, though, you mentioned earlier that there are like variations, optimizations built on top of Paxos.
Yes, there are a lot of them.
Can we talk about those a bit?
Absolutely. So Paxos has kind of inspired a whole family of algorithms, each one addressing specific challenges or improving performance in different ways.
Gotcha. So give me some examples.
Okay. So one example is multi-Paxos.
Multi-Paxos. Okay.
This one streamlines the process for choosing a whole sequence of values.
So instead of running a separate instance of Paxos for every decision, you can kind of bundle them together.
Exactly. Once a leader is established, multi-Paxos lets you skip the first phase of the algorithm for any subsequent proposals.
So that saves time.
It saves time, it reduces message overhead,
it
speeds things up significantly.
So once the conductor has everyone's attention, they can just keep going.
They can just keep calling out the notes.
Without having to, like, reintroduce themselves.
Exactly. And this is especially helpful in systems that are processing tons of commands.
Right, like a busy database or something.
Exactly.
Yeah. What else?
Another interesting one is fast Paxos.
Fast Paxos.
This one's all about reducing the number of message delays.
Okay.
It introduces a new role, the fast acceptor.
Okay.
Which can accept proposals more quickly.
So it's like an express lane?
Yes, an express lane for certain proposals.
Okay.
So if you need really low latency,
yeah,
this can be a big advantage.
That makes sense.
So you have multi-Paxos for efficiency.
Right.
And fast Paxos for speed.
It's amazing how Paxos can be adapted.
It is. It's a very versatile concept.
Yeah, for all these different situations.
It's like a tool that you can customize.
Right, to fit the job.
To fit your specific needs.
Okay, so Paxos has all these variations.
Right.
But its influence goes beyond that, right?
It does. It's also inspired the development of other consensus algorithms.
Really? Like what?
So one really popular one is called Raft.
Raft, okay.
It takes some of the core ideas from Paxos.
Yeah.
And simplifies them. Makes it a little easier to understand.
So it's like Paxos for beginners.
You could say that, yeah.
Okay.
And because it's simpler, it's more readable.
Right.
It's been adopted really widely.
Okay, that makes sense.
So Paxos has had this ripple effect on how people think about consensus.
And are there other areas where Paxos has been influential?
Absolutely. One of the big ones is blockchain technology.
Blockchain?
Yeah, blockchains rely heavily on consensus mechanisms.
Okay.
To keep their distributed ledgers secure.
Right.
And Paxos really provided the foundation.
So Bitcoin, Ethereum, all that.
All of that, yeah.
They owe something to Paxos.
They do. The principles of distributed consensus that Paxos pioneered, those are essential for blockchain to work.
Wow. I didn't realize Paxos had such a big impact.
It's pretty amazing, isn't it?
It is. This whole deep dive has been eye-opening.
I'm glad you enjoyed it.
We've learned so much from how Paxos works to how it's used in the real world.
The real world impact?
And even its lasting legacy.
It's a powerful idea.
It is. It's a testament to, how elegant and robust solutions in computer science can really shape the world we live in.
Absolutely. Paxos shows that if you tackle a complex problem with clear principles and careful design, you can create something truly groundbreaking.
Well said. Well said.
Thank you.
And on that note, I think it's time to wrap up
our
Paxos deep dive.
Sounds good.
Huge thank you to our expert guide.
It was my pleasure.
For taking us on this journey.
Happy to do it.
And to all our listeners, thanks for joining us.
Thanks, everyone.
We hope this deep dive has sparked your curiosity.
Keep learning.
To learn even more.
Keep exploring.
About this amazing world of technology.
It's a fascinating world out there.
It is. Until next time.
See you then.